Ora. Ok, allora, vabbè, chiudo un attimo il professor Casciola da Sapienza e il tema è l'interazione tra i polimeri e i fluidi turbolenti riguardo alla...
Okay, so thank you, Luca. Thank you to the organizers for the invitation. I'm really glad being here. So I was commenting together with our guests, so with Giovanni and the others, that I started my career in a sense here at IAC, when IAC was not in this place, but in another place close to this one. Also another reason why I'm glad to talk to you is that because in recent time I've been involved in sort of different things, so I'm really happy to go back to talking about science. This is an example of what I've been doing in the last days. So I was introducing a hard rock concert in our Faculty of Engineering here in Rome La Sapienza. That was really a very nice experience in the sense that these guys, they are able to produce extremely loud, completely uncorrelated noise, which is something that in the theory of stochastic partial differential equation is of some importance. Anyhow, let's try to talk about the subject of today. So I'm going to talk about the effect of a few amount of dispersed long-chain polymers in a turbulent flow. So probably everybody knows the problem of turbulence is one of the important and solved problems of classical physics. Here you see a few illustration of different kind of very complex turbulent flows. This is what we are interested in mainly as engineers. So what you see is the velocity profile of a laminar flow, a quasi flow, compared to the mean velocity profile of a turbulent flow in blue for the same shear stress at the wall, so the same drag. And you see that the flow rate is incredibly reduced under turbulence. And this means that in engineering application, it's really important to provide tools to reduce the drag of a fully turbulent flow. Now, these polymers are able to do that, but before entering into the specific subject, I want to mention the different alternatives that are possible in technology today. So one is the possibility to use active control. Here you see a pipe in which there are different chunks of the pipe that can rotate, and these rotations of the boundary is probably arranged that are able to reduce the drag. This is an example of active control. On the other hand, there is this passive control, which is bio-inspired, and you see on that slide on the left some micrographs of the shark skin. There are protrusions that are able to interact with the turbulence and reduce the drag. Okay, so this is the effect of polymers. Okay, so what you see here are hoses of firemen. So they want to shoot these jets of water as far as possible, and you compare. You see compared here directly two different jets which are activated by the same pump, one with polymers, the other one without polymers. You see that the length they can reach is increased by the addition of a few parts per million of long-chain polymers. This is another example of application. This is a shot of a picture of the trans-Alaskan oil pipeline in which they inject polymers in order to reduce the drag. Of course, they have to push liquid oil for incredibly long distances, thousands of kilometers, and they want to reduce the power spent in the pumping system, and so they put the polymers in. So those polymers are really very effective. The point is that it's really not completely clear how they work. So how they can induce such a significant drag reduction. And one interesting point is that they do that without laminarizing the flow. So the flow remains sort of turbulent while the drag is reduced. This is very interesting for direct applications, but also more in general, because we would like to understand what is the mechanism in order to try to see if we can extend it to different kind of applications. Because one of the main limitations of these polymers is that they can work in water. And maybe you want to reduce the drag of an airplane, which is flying in air, okay, where these polymers cannot be used, are not effective. So what you see here is the diagram of the friction. It's a friction law. So the lower curve is the turbulent drag of friction coefficient for a fully completely Newtonian flow. And then you see different experimental results for polymer-induced drag reduction. You see that on the vertical coordinate we have we have the reciprocal of the square root of the friction coefficient. So if the curve goes up, it means that the drag is reduced. And you can reach an asymptote, which is called maximum drag reduction asymptote, which is the maximum level of drag reduction you can achieve. This is incredibly high. It could be 70%, even 80% of the standard Newtonian drag. What you see from this plot is that there is an effect of the Reynolds number that you see on the horizontal axis, and you see that for a given solution, at the beginning you do not see any effect, and then when a certain threshold Reynolds number is reached, the drag reduction starts to go up, and then you may play with the concentration of polymers. If you increase the concentration of polymers sufficiently and the Reynolds number is large enough, then you reach the drag reduction asymptote. Okay, so these are issues that I would like to cover a little bit in this talk, because we have been trying to do simulation in order to reproduce this kind of behavior. Okay, so this is what I was anticipating. So the drag reduction onset occurs at the critical Reynolds number. That onset, so the critical Reynolds number is going to depend on the molecular weight of the polymer and on the size of the pipe. The onset is unaffected by concentration. So the concentration controls how much you can reduce the drag, but not the onset Reynolds number. And then, of course, once you reach the onset, if you increase the concentration, then the drag reduction increases until you reach the maximum drag reduction asymptote, so the maximum value that can be achieved at that particular Reynolds number. Now, for trying to explain this kind of behavior, there have been two different and conflicting theories. One is due to Lumley. Lumley, for those who do not know him, is a very famous fluid mechanicist. What Lumley suggests is that the polymers get stretched with a certain relaxation time. When the relaxation time of the polymers is comparable with the large eddy turnover time of the turbulence, then you are going to have a stretching of the polymers, and those polymers affect the turbulence and reduce the drag. This is the idea. On the other hand, there is the elastic theory of Dejean, which states that these polymers are only poorly stretched, and then there is a sort of elastic back reaction. They are stretched, they want to go back, and it is this elastic reaction on the fluid that is responsible for the observed drag reduction. In fact, no one of the two theories is able to fully explain what is observed in the experiment, so it means that there is something else that should be sort of understood. Okay, so I would spend a little bit of time in explaining the models that are used for polymers, in particular the model that I'm going to use here. Probably some of you are familiar with these ideas, but nevertheless, I want to go through them a little bit in a fast way, so to speak. So what we think is that we are going to have a long chain polymer. There is what they call a persistent length in this polymer chain, in the sense that you can coarse grain the polymer molecule with a sequence of links which have a given defined length. Okay, and then in the simplest model, those links can rotate one with respect to the other, such that the probability of the orientation of one link is completely decorrelated from the orientation of the previous one and the next one. Okay, so you have a sort of random walk. You have this guy and you get the random walk. Now, following the standard ideas that you have in this field, you're going to have the probability distribution of the orientation of the single link, which is equidistributed on the solid angle. And then you have very many of these links, and then you end up with a Gaussian probability distribution of what is called the end-to-end vector of the polymer. So you start from the beginning here, you want to reach the end, you define this vector capital R, which connects the beginning of the chain to its end, and then the probability distribution of this end-to-end vector is a Gaussian. Okay, out of the Gaussian, this probability you can build a free energy, and then you're going to see that this free energy as the standard form minus kBt, where kb is the Boltzmann constant, times the probability logarithm of the probability of the BDF. And if you do the computation, you end up with seeing that this free energy is basically quadratic in the elongation of the polymer. So it is a spring. Sorry, it is a linear spring basically, whose energy, particularly this free energy, is quadratic in the elongation. Okay, so this is the starting point. Okay, so once you have that, of course, you recover. This is obviously just the reverse of the operation I was doing before. The probability, the exponential of the free energy normalized in thermal units as it is standard. And then you have a Fokker-Planck equation that is able to reproduce this equilibrium probability distribution function, in which you have the gradient of the free energy. This gamma here is a friction coefficient. The equilibrium result solution for this equation is independent of gamma. Of course, it factors out. And then you have an associated Langevin equation. Okay, so we are sort of reversing the standard way of thinking, right? Rather than starting from a sort of mechanical description, we started from a statistical description of it, went through the Fokker-Planck, and then found the Langevin equation. Okay, this explains directly that you are going to have a mechanical interpretation of what is happening in terms of a friction coefficient gamma acting on the extrema, the beads of this polymer. Then there is a force that counteracts this extension, so the spring wants to collapse back to zero. And then there is a Wiener process, so a white noise term that sort of forces this spring, preventing them from collapsing to zero and keeping it to a certain defined equilibrium average length. This is an overdamping.
And why you find it?
This is overdamped because at low scale, the inertial effects are irrelevant. Everything is dominated essentially by the viscous response, by the friction of this object with respect to the solvent. So this is.
No, but you know the deviation where comes out that this is what you have. I imagine this Fokker-Planck.
So yeah. So if you stop.
How do you derive the Fokker-Planck?
Okay, this is basically the Fokker-Planck for which this is the equilibrium solution. So, okay, you have this, and then you are looking from the corresponding Langevin equation, which was as the corresponding associated Fokker-Planck, and this is the field that you have here, and that field. Okay, so it's a sort of reverse way of thinking, if you wish. Okay, so you're going to have this Langevin equation. And this leads you to the mathematical model that we need in order to do the computations, basically. So you end up with this idea of dumbbells. So you have these dumbbells, so these beads, which are the places at which this friction is with the solvent should act. And then there is a spring which connects the two springs. Now, if there is an external flow in the solvent that tends to stretch those dumbbells, okay, the spring is extended. You're going to have a friction which counteracts this extension, basically, right? Now, it's important to notice that in that system, you are going to have a characteristic time scale, which is the relaxation time of the polymer. So if you fully stretch the polymer and you let it go, it will recoil with a certain time scale, which is given by this expression. And what was important for us is that this relaxation time is directly related to the physical properties of the polymers, in particular the number of links, the size, the dimension, the length of the link, and then of course there are the thermal units over here and the friction coefficient. Okay, so these are sort of chemical properties of the polymer, whereas this friction coefficient can be directly measured from experiment. Okay, I will show you some results later on. Now, if a velocity field is present in the solvent, the friction will be the friction force will be proportional to the velocity of extension of the spring minus the velocity difference of the fluid at the two beads, basically, right? Because the friction is related to the relative velocity of the spring of the beads with respect to the background flow. Okay, so you're going to have an object like that, which is essentially the same that we had before, except that we are adding here the velocity difference of the fluid evaluated at the position occupied by the two springs. Okay, so this is what you have. You have the system in a certain state, you extend it, and so on. This is basically the fact that that you are doing a force balance on the two beads, which are connected by a potential that could be linear, as in this case, or you may generalize it if you wish. And what I was trying to highlight here is that you can solve the equation in principle for each separate bead, and this can give rise to important effect related to segregation. So if I'm going to have the two beads here and the velocity is different, then this object can segregate following the fluid in different way, because one bead can be trapped into a vortex, so to speak, the other one into another one, and then you may have, in principle, some sort of very complicated effects. Okay, so this is the bead and spring model. What are the pros for this? The model is obtained by coarse graining the physical polymer chain. This is important because there have been previous models for this, in which you have effective parameters that you cannot directly connect to the physics. So you can tune them in order to see what is happening, but in this particular case, given the specific kind of polymers, you are able a priori to find what are the parameters that you need to enter into the model. And this for us was really, really very important. Okay. Another important point is that the model is simple. I mean, it's just a string, nothing more than that. As a con, you have the fact that you have to follow each single dumbbell. So in principle, each single polymer chain you have in the top. There may be too many. We will see what is happening here. Then there is another aspect. For the model, as I was discussing it so far, the model free energy is rather poor. It is just elastic. It means that the spring can be extended indefinitely. Can become as large as you wish, right? Which is not true, of course. Okay. So either you have a better approximation to your free energy, because of course in deriving the Gaussian approximation, you're doing approximation actually, and you end up with something that can be extended indefinitely, or you force a limiting extension, so you know what the contour length of the polymer is, and then you put a correction to the elastic constant, so to speak, making it an hardening spring that cannot extend exceeding a certain maximum. So this gives rise to what is called a finitely extensible nonlinear elastic dumbbell, which is the object that we are actually using. Okay, now we want to couple this with the solvent. Okay, so there is the center of mass of the polymer, center of figure, more probably, because there is no actual mass.
You have still the Gaussian? No more.
No more if you put the nonlinear. No. You don't have all the people. Yeah, but you still have this object, right? You can still write the. Sorry, where I am. It's moving.
No, because with the Gaussian, you know the focal length.
Exactly.
But with the non-Gaussian,
you don't. But you still have the Langevin kind of equation. So you are going to have a stochastic differential equation.
You don't have any more. Why you have all the same?
Because you just so in a sense you just postulating it. So you want that. Let me see if I can go back to where I want to go here. Okay. So you still have an equation like this, in which you have the relative friction at the beads, the recoiling force, which is now the derivative of free energy. You have a model free energy for that. You can do some numerics in order, if you want to fit this free energy from the result.
I understand that you got good there.
Yeah.
But once you don't have any more the Gaussian for the station illusion on the focal plan, you have a focal plan.
Sure.
But it's more
complicated.
And then you have all the same this form of the Langevin equation.
Yes. If you wish, you can start the opposite way around. But if you postulate, we go back to here, if you postulate the free energy, all this stuff still works, right?
So you assume this new free energy, and you say the dynamics will be the same, but there will be an extra sanction. You know what the right?
No. You say assume you know the free energy. We are modeling it, but assume somebody gives you the free energy. Then you know that your equilibrium probability distribution is this one, where F is a function of R, which is no more Gaussian. And then you're going to have a Fokker-Planck equation in which the drift coefficient is more complicated than before. Instead of being linear, it's a linear function of the extension, right? And again, from this Fokker-Planck, you're going to generate, or there is a corresponding, if you wish, Langevin equation in which the drift is a nonlinear function of the extension. So the thing is consistent. The only point is that in general, you don't know the true free energy when the system is nonlinear, so you have to model it. That is what we did by assuming that there is an hardening spring such that the spring constant increases with this extension up to a point that the polymer cannot extend more.
But in this case, you don't know what is the probability is always given by the FENE.
Yes, yes.
By the model.
Yeah, yeah. Okay, so yes, I think I was here, right?
Yeah.
Okay. Because it is responding with a certain delay and I'm too fast. Now I will do it more slowly.
One dumbbell per polymer, but the polymer is a lot
of links.
And so why
you don't care of the others?
No, you seem to care about that you have too many dumbbells, but the dumbbell is already a very coarse-grained description.
Yes, and then okay, so the dumbbell is the coarse-grained description of the macromolecule, but then you have many macromolecules entering dumbbells.
So you want to go even more coarse-grained?
No, I don't want to be more coarse-grained. The coarse-grained is at this level. I just want to have many molecules suspended in the flow. Okay. So for the moment we were focusing on a single macromolecule. I will have a solution of that.
Why is the
Oh, the con is too many. What do you think?
Less than that, I mean, we do
okay.
Full polymer to be only.
Okay, I want to give you an idea of that number. That number is 10 to the 9. It is too many or not? To me, if I want to do a computation on a computer, too many, 10 to the 9 objects follow into a turbulent flow, that is too many.
How do they interact?
They interact with the flow, not among themselves, because the solution is diluted.
And then they're independent. So
yes, but there is the flow. Wait a second. There is a turbulent flow that couples them. Okay? So the single macromolecule just perceives what happens near to.
So you cannot reduce in the model the number of the.
No, not in this. You really need that. I mean, you can invent something, but then it's cooking, right? You can cook whatever.
You know that now about the number we don't care.
Yes.
Okay. Because we can.
Yeah.
We find it. Yeah, there could be something similar, but if the scale, the length is very long, the interaction to the fluid, then you cannot.
Sure.
You cannot.
Okay. So let's see what happens next. Good. So now you want to couple this dumbbell with the solvent. So you are going to have a transport equation for the center of mass of the dumbbell, which is transported by the fluid velocity. Why this? Because these molecules, they are very long, so the diffusivity constant of the center of mass is practically zero. You can put a little bit of Brownian motion over there, but it's completely irrelevant. Then you have the equation for the elongation of each single dumbbell. Okay, and the only thing that changes now in the evolution equation for the probability distribution function is that the right-hand side is the same as before, but now the time derivative should be done following the motion of the center of mass, that is following the motion of the fluid. So this is what in fluid mechanics we call a material or total of derivative of the probability with respect to time. Okay, now once you have this thing, you can obtain an equation for what is called the conformation tensor of the dumbbell population. So the conformation tensor is the average of the covariance matrix of the population. Okay, so this is the tensor product of the elongation of one molecule with itself, and it is average in a statistical sense with respect to the probability distribution that you have here. Okay, and from this, just by doing an elementary integration by parts and integrating, you can extract an evolution equation for the correlation matrix, and the equation looks like this. So you have a term here which is related to the velocity difference. And then there is the effect of the forces acting on the beads, and then this is the equilibrium value. If you remove the forcing, which is the velocity field here, and you leave the system relaxed, you're going to find that this thing gets equal to that. It relaxes to the equilibrium state, which is an isotropic state for the population. So its number is oriented, independent of whatever, right?
Question. The first step is this derivation is done using that equation for our dot. Correct?
For P.
For our dot?
For P.
No.
This is a,
There are two elements.
yeah,
One is that R evolves with envelopes.
yes.
The fact that you're taking
Yeah,
the
yeah,
central
sure.
product is semantic. But
Yeah, sure.
okay.
Right.
But then the average is taken on P of T
With respect to P.
with P of T.
Yeah. P of T and X.
Or the initial.
No, the current one. P of X and T at the current moment.
So you have to differentiate both R and P to the right distribution.
No, not truly. Because what you have to do, I think I need to, I don't know, now for the people, I assume that there is someone connected remotely, but.
The camera is.
So they can, okay. So when you evaluate that object, this average,
Yeah.
what you have here is an integral of the thing you want to average with respect to P. And then you have to integrate with respect to the phase space. Okay, now if you take the derivative of this, the only thing that depends on time is this one. So what you have is R tensor R, P dot as this right hand side. You substitute, do the integration by parts, and you end up with this.
You have R of T, no?
No, because this is what we call, I mean, I don't know if the language is universal, we call this something variables. There is no dynamics there. The dynamics in the probability. Okay? I think this is what you do usually.
No, usually and even you could even transport.
Yeah, if you wish, you could write. Yeah, you could, but this is the way.
So you don't use R-dot.
No. Okay, so you end up with this equation for the covariant matrix. Now, if it happens that your springs are linear, and you linearize also the velocity difference, taking it as a constant velocity gradient times the separation, this is going to be to produce a Gaussian solution. Okay, and then all you need to know about the polymer population is the correlation matrix. The average elongation is 0, and you want the correlation matrix, and the correlation matrix is the solution of this equation, which is closed in that particular case. Okay, this is going to give rise to what is called the Oldroyd model for polymers, which is very well known to people working in rheology, for instance, right? Okay, now, when you have also the solvent, you are going to have the condition of incompressibility for the fluid, and then you have the Navier-Stokes equation for the solvent component, and this solvent interacts with the polymers in the sense that there is a localized interaction within the force exchanges between the particles and the fluid. So you're going to have a sequence of Dirac delta function that are forced in the Navier-Stokes equation, which is not something really, I mean, it's a little bit nasty, so to speak. I mean, the mathematicians will sort of raise their eyebrows, right? Nevertheless, we go on. What
is worrying the mathematicians?
Oh, the mathematicians are worried simply by the equation in this part. And then you force it with a singular forcing, and they get crazy usually.
But it's possible to formalize. But clearly, already Navier-Stokes equation is complicated now. If you have the Dirac masses, first of all, you have to solve the equation.
Yeah. So I mean,
completely easy.
Yeah, it's something that, I mean, we close our eyes and
it's
keep on
possible to write the formulation, the correct written formulation of the equation. Yeah. To solve it,
it's another issue. Exactly. Okay, so now you may want to see whether this object that is here can be rewritten or reinterpreted in terms of a stress tensor. Okay. So locally, you can take the standard average with respect to the polymer population. You work with that. You're going to have a sum over the beads of the reaction force localized at the position of the beads, but each bead is formed by each dumbbell is formed by 2 beads. So instead of summing over the beads, you may sum over the dumbbells, and then you have a sort of dipolar force, okay, which can be Taylor expanded. Okay, and this is, I mean, a standard thing that is done in Kirkwood, Irving kind of stuff, right? And then you do it. I mean, I don't pretend you follow that. That is not really important. But the final thing is that this extra stress is an object which is related to the local concentration of the polymers. Then there is a conditional average of a tiny object, which is a long correlation within the elongation and the force applied to the polymer. Since those polymers are very small usually, a standard approximation is that you throw away everything and you are happy with the first contribution. Okay, this is the standard approach. Okay, and then if you do that, this extra stress is basically related to the correlation matrix, the conformation tensor of the polymers. If the system is linear, the constant is a constant. So it's simply that, and we already have the equation for this correlation. Otherwise, you have to take into account the fact that there is this dependency of the constant, spring constant on the elongation. Okay, this thing was done. This Giovanni maybe may have some comments on that. For what I know, in this particular context, this idea was put forward by Kramers in 44, and then the general theory, I think, was developed by Kirkwood and Howard, but I don't want to enter into the history of statistical mechanics.
But Kirkwood died in 59.
Was 59?
Yeah.
Okay, this yes, but when I think when he applied these ideas to this particular case, to this model, I think it was 67. At least this is the reference I found. I said I don't want to.
A bit bizarre because 8 years after he died, he still was publishing. Was an efficient man, but
he died. You said?
He died.
No, I'm sorry, I didn't know.
He died.
He died. So this reference is wrong. This is what you say.
I don't know.
Yeah, this is what I found in the book of Berg. Sager, Berg, and the other one. Yeah, it's this very famous book in polymer physics, right? He gives this reference, but I don't know. Okay, I will pay attention to. I mean, maybe he was having a sort of spiritistic, I don't know what, and then wrote a book after that. But he died.
In the book, they reported the result.
No, this was the actual reference. Good.
No, that's right.
Good to know. Okay. Then, in the cases we are interested in, the concentration of the polymer is constant, so they are homogeneously distributed. We were looking at those effects of segregation that could produce a sort of clustering. We never found it. So for us, still, the concentration could be considered reasonably constant. And then what you do, I mean, this is a stupid thing. You want to extract an equilibrium contribution to the extra stress, and then add and subtract. The reason is that this is isotropic, so it is a pressure. You just add it to the pressure of the solver, of the Newtonian solver. You have to use a projection method in the numerics to find the pressure, so you don't really care about this guy. It is there, you will find it. Okay. The real part that matters is this one. Okay, so with this, you end up with these Oldroyd or FENE-P models, and this is written in a synthetic form, so to speak. You have this extra stress of the polymers that can be written this way. You have the evolution equation for the conformation tensor, and you have the equation for the Navier-Stokes equation. Okay, so this is what you wanted to have. Instead of following each single model, molecules, now you have a sort of rheological constitutive law that connects the stress induced by the polymers on the solvent to this conformation tensor, for which you have a closed form equation. The equation is in closed form if you are in the field of linear springs, so Droid model. When you are in the FENE, non-linear, you have to introduce a closure assumption. And the closure assumption is that to assume that the elastic stiffness of the polymer is an effective one, which is evaluated at the mean square root elongation of the population. This is called Federlin's approximation. It is true, it is not true. This is the thing how we vote. The reason for that in practice is the following. If you do a Droid in a turbulent flow, the system diverges because the turbulence is able to stretch those polymers to infinite, and then your computation blows up. Okay, so you have to control the length. So you enforce a finite length, but then you have to close the system because, of course, then this equation becomes so linear, and you cannot do it with that, right? So this is the FENE-P model, and this is the reason why it does not work. All the computations have been done usually. people still doing this computation with this approach. Why it doesn't work? Because basically what you are doing, you are approximating the solution for your polymer population in Gaussian form. You are changing the stiffness, but the stiffness is constant, so still you are going to get something which is Gaussian. So if you reconstruct the elongation of the polymers, you find these curves over here. And this is the maximum extension of the polymers. Okay, now, if you run our models, I will explain how it works, you get something like this. You get a sort of plateau, but what is most important is that there is a big component of the polymer population which is enormously stretched. You see, this is the probability distribution of the elongation of the polymers, and then you see that this an important fraction of the population is extremely stretched. So R is close to 1, which is the maximum. Okay? So this is really a very big difference, because what it's saying is that in the classical approximation, you keep your molecules get stretched, so they can accumulate a lot of elasticity. What is happening here is that they have an asymptote, they reach an extreme length over which they cannot be stretched anymore, and then the viscous interaction with the solvent becomes extremely strong. Okay, so this is the main difference. Okay, now the point is that how do we solve the dynamic Stokes equation? And for doing that, we have to regularize the solution. So what we do, we assume that the velocity of the solvent is decomposed in two contributions. One is related to the solvent as no polymers were there. And then there is a sort of perturbation induced by the force that the polymer exerts locally. Okay? Now, if you look close to the polymers, so the dumbbells, the subjects are really very small. So the local Reynolds number is the relative velocity with respect is small. And as a consequence, the Reynolds number locally is very small. And then you linearize, simply you linearize the Stokes equation there for this perturbation. Now you end up with the Stokes equation for the perturbation velocity, but now it is time dependent. Okay, this is really important because there have been a lot of other attempts in which they said, well, if inertia is irrelevant, then forget also about the time derivative, and you are going to have the steady state Stokes equation. This is a nightmare. The reason for that is of course the fact that the steady state equation, they are elliptic. So if you perturb the field at a place, all the field persists this change. And then if you want to do the interaction between the polymers and the fluid, you get crazy. I mean, the number of interaction increases dramatically, you cannot do it. Okay? Instead, if you're going to use this, you can sort of solve step by step. So what you do, you advance a little bit the solution, then you advance the perturbation by a step, add the previous solution with this perturbation, and start all over again. Okay, so you are in a position in which, step by step, you are solving just the initial evolution of this equation with the localized forcing. It means that the perturbation is localized in space. Okay, not truly, because there is the divergence left condition on velocity. But then you play a little bit with the irrotational solenoidal part, you play a little bit with this stuff, and then as a consequence, what you can do, you can solve for a sort of pseudo velocity, which is just the convolution of the forcing with the localized Gaussian, which is very narrow. Okay, then it means that the single polymer interacts only with a very small neighborhood of the solvent. Okay, and then what you have to do, you have to introduce the correction for solenoidality, but you don't care about that because in the Navier-Stokes equation you always have to do that. So you couple all together and then do the projection on solenoidal fields, and then you're going to recover the entire velocity field in the entire domain with a very limited cost. And this is the reason why we could really go up to 10 to the 8 molecules. Okay, this is the result. So the combination of this sort of theory together with this, I would call it a trick to solve it, allowed us to follow one single molecule in time with the first screen model, of course. Okay, good. So well, then we had to do something to regularize the solution. I mean, if you're interested, you can find something in this paper, but we can also discuss the details for that. Okay, now the point is the following: you are going to solve this equation in which you forget about pressure. You recover the pressure by projecting on solenoidal fields later on, and then you're going to have a forcing which is those particles that represent the molecules that move around. Okay? As they move around, they release a little bit of vorticity. Then they move over, right? So at the present time, the production of vorticity is very localized. The vorticity that was released at the previous instant of time diffuses. The previous step also, this is going to diffuse more, and at a certain time, with a certain delay time, you are going to see the vorticity into the grid over which you are resolving the Reynolds equation. And the nice thing is that if you go into the details, you can do that without losing momentum. Okay, so this is perfectly conserving the total momentum, because there is a certain amount of momentum which is associated with the vorticity that you're not resolving, which is hidden, but it's still there, and it will appear at a later instant into the field. This is important because otherwise, I mean, you are going to lose momentum and the thing doesn't make any sense. Okay, good. Now, what can we do with that? We go to the web page of a factory firm that they start out. They sell things for firemen, and they provide the information on the kind of polymer they inject into the hoses, right? So we selected one of those and wanted to do the simulation one-to-one with the concentration and the molecular weight of the polymers that they are using in practical applications. This is in a particular example. This is this polymethyl oxide. This is the molecular weight. It's a very long chain, of course. The link is this side. The number of link is 10 to the 4. So you are really in the condition for which you can do the constraining. I mean, it's a very long molecule. Okay, and this guy has a relaxation time of 5 times 10 to the -2 seconds. So it's relatively slow. This part is important because it allows the chain to couple with the time scale of the turbulent flow. Okay, next. This is an experiment, very clever, very good one. Choi et al., this physical review letters 20 years or more ago, in which they did something very precise. So they use a DNA. The reason why they want to use DNA is because they can control the length precisely. Okay, so you see now the typical properties of this particular polymer, and the reaction time is now 1 second. Okay, now with this DNA, they can do stretching experiments. So they can take optical tweezer, they stretch the polymer, release the polymer, and look at what is happening. And then they find a spectrum of relaxation times. You see that the principal one is at 1 second, and then there is the rest of the chain that, of course, relaxes with the faster time scale. Okay. Now, what matters when interacting with the turbulent flow is this one. Probably also the second could be important. Okay, we are doing some numerical experiment with multi-bead chain in order to see whether the spectrum of relaxation time plays any role in the interaction with the turbulence. Okay, but the result I'm discussing now are just the single relaxation time, the principal one, the slowest one. Okay, so this is a sort of the model I wanted to set up in order to understand what happens. So there is the previous Langevin equations. There is the nonlinear elasticity associated with the finite extensibility of the chain. And then the model pretends that there is a velocity difference across the polymer, which is a combination of something which is regular, goes like linear in the separation. We are sub-Kolmogorov in scale. And then there is a transition which is not described, that you enter into the inertial kind of regime. So this is a combination of a linear law on separation with the classical 1/3 behavior, which is typical of inertial turbulence. Okay. Now we use this object in a one-dimensional case for which you can solve this equation in an elementary fashion. You do it, and you find the equilibrium probability distribution function. Okay. Then you can connect the Kolmogorov scale with the velocity gradient. They are strictly related the one with the other. And then this is what you see. If you increase the velocity gradient, this toy model tells you that the population of polymers will respond by accumulating, sort of condensing, at the maximum allowed length. Okay, this is very important because confirmed, at least, gave us a sort of understanding of what we are observing in the actual numerical simulations. Okay, and then we go to the actual simulations. So in this particular case, I'm discussing two simulations. One at Reynolds number 180. The second one was 320. The Weissenberg number is the ratio between the relaxation time of the polymers and the flow time scale. This Weissenberg number, we had it ranging from 0 to 10 to the 4. 10 to the 4 is completely realistic, but we wanted to push to that because all the other approach, the one based on FENE-P model, they have big problems when the Weissenberg number increases. The reason is that the equation has an hyperbolic underlying structure that it drives you crazy when the relaxation time becomes very, very small. Okay, so we are able to go from 0 to 10 to the 4. As I said, 10 to the 4 does not exist. Standard application, so the trans-Alaskan oil pipeline, it goes at Reynolds Weissenberg number between 1 and 3. The O's of the firemen, it goes to 10, 15. And 10, 15 is still very high. You cannot do that with the FENE-P already. Okay, and then we wanted to compare. Now, we have 10 to the 8 objects. We have the grid to be resolved for the turbulence. Everybody, more or less everybody knows how demanding is solving a fully three-dimensional turbulence. So, of course, then you need significant high-performance computing capabilities. And then we are happy with Sinega, with the fact that they are starting out the new Leonardo facility, and then they offered us some time in the pre-production phase of the system. So we had the opportunity to run for free, which is something. Okay, and then we explored that possibility and performed a few simulations. So this is an example of what we have. This is the mean velocity profile. The black is the Newtonian, and the purple one is the polymer solution. You see this increase in the flow rate for given pressure forcing. So this means that indeed you are observing drag reduction. So I'm not going to describe this. This is the distribution of the average stress across the channel. Probably it's too detailed for your interest here. And then this is the behavior of the percentage of drag reduction that we achieved at increasing the Weissenberg number. Okay, so as the Weissenberg number increases, then you start from something which is unable to produce a significant amount of drag reduction, then you go up, and then you saturate about 27% of drag reduction in this particular case. And this is the behavior of the polymer population. And you see that if you go up with the Weissenberg number, look at this 10 to the 4. As I said, this is unrealistic, but look at the PDF. All the polymers are fully stretched, right? It means that they cannot be stretched more. So if there is a sort of eruption in the turbulent flow, so a strong extensive gradient, right? The thing cannot comply with that, and it starts dissipating locally a lot, and it dissipates selectively. So it only dissipates when the thing is already stretched, and when there is an elongational kind of stretching, and this happens usually for those who are familiar with turbulent wall boundary flows. It is the typical kind of event that takes place during what we call the regeneration phase of turbulence. So the logarithmic layer of the turbulence, the buffer layer of the turbulence, has a relatively well understood kind of dynamics, and there are phases in which there is a strong explosion towards the exterior. And it is there that this particular part of the population of the polymers is interacting with the turbulence, so it depletes this eruption event, and the consequence of that is that all the structure of the field changes. In particular, the transversal correlation of the field becomes much larger, and the turbulent reproduction phase moves away from the wall. The consequence of that is a reduction of the mean shear at the wall, which brings about the reduction of drag. Okay. This is again to try to visualize. Probably it's too detailed, but for different Weissenberg number, what we see here is the probability to find an elongation that is larger than a given threshold. Okay, so if the threshold is 0, all the population is longer than 0, of course, right? And then you see that there is this plateau here that at large Weissenberg number ends up at 99.9% of the total length. So in this plateau here, almost all polymers are basically fully stretched. Okay. Good. This is another way to try to understand the kind of results. So in a physical experiment, you cannot do much except observing. Here we can interact with the system. So we can do a sort of selective decimation of the polymer population. We follow the polymers, but allow them to backreact on the fluid only when we wish them to do it. Okay. So what we do, we remove the less elongated polymers. Move out a little bit of part of the interaction with the population which is poorly stretched. And then we keep on increasing the percentage of population that is removed. And then you see that the drag stays constant, stays constant, stays constant until you start removing objects that are elongated more than 99.97 of the maximum elongation. When you reach that, the drag reduction starts to decrease. This tells you precisely that it is only the population of the polymers that are stretched between 1 and this almost 1 number that matters for drag reduction. All the others are completely irrelevant. Okay, now this result in terms of interpreting experiments is crucial because there has been a lot of discussion because the people using DNA, very controlled in length, found a certain kind of result. The others, with the other kind of synthetic polymers, they are polydispersed. And they couldn't find any agreement concerning the concentration, right? So you needed a lot of more concentration for the PEO kind of polymer with respect to DNA. And this doesn't match with the similarities with the two kind of polymers, right? And the reason is that is the polydispersity, okay? The experimenters, usually what they can do, they just weight the amount of polymer they put, but if that is polydispersed, they have no control of that, okay? And then this is what we did by showing that indeed you can reproduce basically all these kind of results. This is what is going to show. I don't want to enter into the details of this figure, this result, but what it says to us is that to reproduce the back reaction of the polymer, the actual back reaction of the polymer, which is the black line, you only need to take into account the almost fully stretched polymers and assume that they react with the dissipation. So the exchange of force is the friction times the velocity difference. And you see that you follow almost perfectly until you get here at very small intensity of the forces. So this tells us that indeed it is the viscous kind of reaction that matters. And then if you work with the expression for the polymer stress, you end up with a sort of viscous kind of constitutive relationship in which you have a viscosity and the gradient of velocity. But the important point here is that the concentration that you have there is not the concentration of the polymers, it's the local concentration of the fully stretched polymer. This is why it is rheologically so difficult to reproduce the actual behavior, the actual effect of those polymers. Because now I think I show you how this viscosity kind of behaves. You see this extremely intermittent. This is a comparison between the concentration of the elongated polymers with the observed local viscosity. And you see that this thing is extremely intermittent. So these objects, they act only locally at certain particular places that are strongly correlated with the velocity gradients. Okay, then
how do you define local?
By this definition. Oh, sorry. Okay, let me try to synchronize. Okay, with this one. Okay. So what you see is that you
this one, but I don't see
this.
Okay.
Okay. So you start from the Kirchhoff kind of thing, then you take into account the stretched polymers, consider the local concentration of polymers, and then you have the velocity gradient on those polymers. The reason why we can use it because we are showing here that the thing works. Okay, then you have this definition, you can use it, and then this is the thing you find. Okay, so that viscosity field is extremely intermittent, and it's half the model, of course. Okay, next. Next, we want to compare our model with the standard FENE-P, and you see that there is a significant kind of discrepancy. So the two things are different. Okay, This one difference. These are the two models played with the same parameters, basically. This one thing. Second thing is that, as I said at the beginning, we can tune our model exactly to reproduce a specific polymer solution. So there is a one-to-one correspondence between the parameters and the physical experiments you want to do. Okay, now this is very nice. Not from the study point of view, probably, but this is the experimental result by Berman. This is one of the few reasonably well controlled experiments that provide the friction coefficient as a function of the Reynolds number. And these are our computations. And you see that we are starting to follow that. And then at a certain Reynolds number, increasing the concentration, we sort of go around the experimental solution. Particularly interesting in this is this latter point here. Okay, I was putting my finger. This particular point here. This was really one-to-one correspondence with the experiment, so the agreement is reasonably good. And then what you see here was those effects of decimation. Okay, removing the polymer. Right? If we remove the stretched polymers, we go down here to the laminar kind of thing. Okay, if we keep a little bit more of stretched polymers, you increase, you increase, you increase. And this is the effect of concentration. You start from small concentration, almost on the Newtonian kind of behavior. Then you increase the concentration, the thing starts going down. Okay, of course, here you go above Berman's solution because that was at a certain concentration. We were increasing. Okay, well, this is more or less the same kind of thing. I think it's time to come to a close. So summary, we are sort of trying to produce a realistic FENE-P model of this is very difficult to. Okay, sort of realistic kind of model. So we can have the friction coefficient taken from experiments. The elastic contrast comes from the physics of the polymers. We have a given contour length. We have the actual concentration that we find in the experiment. Then we run the experiments. And for instance, we are able to find the proper amount of drag reduction at 0.8 weight part per million of DNA, which is the case for the more precise experiments that have been done up to now. The behavior of the polymer population is highly non-Gaussian. We have seen that this sort of condensation high stretching. We had to use this approach that we invented a few years before for coupling those particles with the Navier-Stokes equations. And then I'm here trying to define a sort of experiment that can be really performed one-to-one with one of our simulations. So you need a 2 millimeter diameter pipe, should belong at least 2 centimeters, and you have to push your fluid with the pump able to perform 2 or 3 bars. This experiment can be done, and we are planning to do it, but not for the moment. Okay, perspectives. We want to perform a deeper analysis of moderate Weissenberg number. Up to now, we are focusing on the highest Weissenberg number because those particular cases were not reachable by the standard models. Now we want to work with the Weissenberg number under 1. We are extending this approach to multi-bead chain. Some results have been appearing recently in this paper. These polymers have a nice kind of behavior because then when they get stretched, they expose more surface to the solvent. So there is a sort of hysteretic kind of behavior, which has been studied very deeply by this group of Hoffman and Jacques for the single chain. We are wondering whether this sort of hysteretic kind of behavior may have an effect in the turbulence. Because when you get stretched, you remain stretched, and before stretching, you take a little bit of time. This one thing. Then another thing we want to do is to do what we call a scale energy budget. This is very complicated, let me say this, complicated kind of computation we try to do. I don't want to enter into that. It will take too long. Then there is a problem with this object. And the problem is that this polymer degrades under strong shear. So if you put this polymer into a pump, a rotary pump, is breaking the chains, basically. Okay, and these particular polymers usually they are covalently bonded. So when you break them, they do not reform spontaneously. Okay, you have to put them into, I mean, you have to heat them up or put some catalyst, so this is something that you cannot do, right? And then there is a degradation of the properties, so that the drag reduction performances reduces. And so one is interested to study linear aggregates that are able to break and reform. And these are surfactant micelles. And this is something we have been starting to work together with Giovanni, who suggested a line of coupling certain kind of statistical mechanic tools together with Jean-Paul Ricaert. This is just for Giovanni. The code is presently running. It takes extremely large and long simulations. Okay, so with that, I don't know, maybe you have been interested at least a bit. Thank you.
Questions?
I have one. How your result compare with the two competing theories of the Gen and the other?
Okay, so the basic idea is that the Gen is completely wrong. And this will make you happy. The Gen is completely wrong. Lamley was closer to reality, but the point that we found is that what matters, let me go here. So I'm moving in the wrong direction. I cannot, I mean, this is the beginning. I know it was the end.
So the beginning,
Beginning, end, I don't know what is happening. But it seems I cannot.
You will not do any ordered procedure.
I do it here. But I'll do it here. Now it's much more under control, at least. No. Okay, doesn't matter. I don't seem able to go back. Anyhow, I was showing to you this extensional viscosity, right? Okay. There is something which is basically lambda is the ingredient. So there is a viscosity times a velocity gradient, viscous response. But the point is the prefactor. And the prefactor is the local concentration of stretched polymers. And that cannot be, I mean, you do not have any kind of solvent mean field theory for that. Because this thing is completely fluctuating. So in this sense, also Lyman was not correct. It was closer to being correct than the Gen was, but the problem is more complicated than it
couldn't be correct because you couldn't predict what was this partial information.
No, because in his model he said there is a concentration, the concentration is C0, all the polymers can behave the same way, go ahead. And the result is completely wrong if you do that in quantitative terms. So the physics is true, it is the viscous effect of those stretched objects. But the point is that the field of stretched polymers is particularly regular and wide. And then this is an ingredient that if you want to match the numbers, it is really important.
So you need to have a system that is not homogeneous.
Yeah, exactly. You have to leave each polymer behave like according to the local kind of force it is subject to. Yeah.
It is this variation.
Domanda di Scagliarini pure, Giovanni. Domanda Scagliarini,
But it's, do you have, not to do this comparison with the experiments, do you introduce some sort of a regularized effective mass of frequent of beads, or is really the mass of the...
There is the actual zero mass of the beads. Over time, not the change. Because I mean, the inertial effect they really do not matter if you do a little bit of.
And so with 10 to the 8 or 10 to 9, it's which one would be able.
Yeah, we are following really all. I mean, it's a model, yes, but 1 to 1. And the point is that, as I said, when you start with the FENE-P model, which is the standard kind of approach, you have to input effective parameters. This one thing. But then when the Weissenberg number goes high, you enter. I mean, probably some among you is working in magnetohydrodynamics. So you have something here that is close to Alfvén waves. So the equation for the conformation tensor is an hyperbolic equation that supports wave propagation. Magnetohydrodynamics is basically the same theory, only with vectors rather than with tensors. Okay, and then you are going to form this object in which you form strong shock wave at extremely small scales. I mean, it's a sequence of these things. And of course, with the field kind of approximation, you cannot follow that, and unless you put into an enormous amount of artificial viscosity. Okay, this is Lagrangian, and then you don't care. You follow whatever they are, and then you form, in a sense, they form the sort of caustics. You simply have two polymers with different length that get closer, but for you, that is not a problem.
What is the effect? You compute the backreaction of the polymer on the flow field. What is the impact, influence of this local forcing on, for example, single point or 2 point statistics, like df of velocity, df of the velocity difference?
We have not looked into that. We're not yet looked into that. The reason was, I mean, we are planning to do, I mean, for doing that, you need to do homogeneous drop turbulence. Because, I mean, in principle, you could do it also on wall-bounded, but you get crazy, right? So you need something more, in which your statistics is better under control. So we are, I mean, starting to use the three-periodic version of the code to look at that kind of things. But at the moment, we have not yet seen that. We have some information, not on the polymers, however, on the transport of massive particles. So with the massive particles, you see that there is an effect into the tails of the spectrum, for instance. We are just looking at. Say it again?
Massive inertial particles.
Inertial particles, yes. Inertial particles. Yeah, with backreaction. And then you see that there is a significant effect into the subcolmograph part of the spectrum. So we are only looking at the second-order statistics and the spectrum in particular. And then there is also an effect on the large scales. So there is a modification of the spectrum on the large scales and on the small scales, and there is an inertial part which more or less doesn't perceive any effect. This is something that people start to see concerning particles also in the experiments. So there is a smart guy in ATH, Filippo Coletti, who is doing very interesting experiments with massive particles, transport of tracers, and these kind of things. And he has a very interesting experimental results on that.
It would mean that massive particles, which are, you have a back reaction, but they are point particles.
Point particles, yes.
This means already the experiment is very small. This means that even if they're so small, they have large scale effect on them.
Yeah, they can. And the reason is that I believe some of you are familiar with that. You have clustering effects. So these particles segregate. So they form large structures, even though they are small. The spatial distribution of the forcing is on large scales, and this was for us was a little bit of an issue, because since we are detecting this effect on the large scale, when you do homogeneous isotropic turbulence, the large scales are those on which you put the forcing. So it is very difficult to understand if there is a direct interaction with the energy injection process, right? So it's complicated. But there is no, for what I know, there is no other ways. I mean, we try to do something with a homogeneous shear in which you do not have an external forcing, but still it's not able to do that.
I have a question.
Yeah.
So there is a local clustering of these polymers inside the fluid.
Not of the polymers, of those who are stretched. So the number of polymers per unit volume is the same everywhere.
I don't understand in this context why the polydispersity is affecting so strongly the phenomenon.
Oh, no, it's not affecting that. The point is the following. So if you assume that you have a binary population to make things simple, right? One is long, the other is short. The short one does not do anything. All the result comes from the long. Now, if you, as an experiment, come to me and tell me, I put a certain number of grams of solution, the nominal weight is the average,
Okay.
you obtain a completely different result. Because you have less polymers, much longer.
Okay.
So if you do that, then you start matching the experimental result. So the explanation is very simple, but first you have to see what is happening, right? I mean, unless you are some visionary kind of guy that can. Okay, but Lamley was discussing this a lot in his papers.
But anyway, weighted average, good. In the sense, if I don't take the uniformity, but I consider the frequency of the long and short, etc., then something meaningful, I have to know also the efficiency of the intervention.
No, but the point is the coupling with the turbulent flow, which is extremely intermittent. So not only counts the length of the polymers that you may sort of recover, but also counts the fact that locally at a certain instant you have something which is flowing up, and then there is a quiescent phase. And it's this coupling that gives rise to that sort of very, very intermittent kind of response to the polymers. So this is the interaction with the turbulence. In fact, what happens is that if you consider the effect of these polymers in a laminar flow, they anticipate the transition. So they seem to be opposite. So they seem to favor the transition toward the turbulent field, but once you have the turbulence, then they deplete the intensity.
Sort of elastic turbulence effect.
That could be something. This is another thing we are starting to investigate. So we want to see whether we can go to the elastic kind of response, which is not for drug reduction applications, but there are many other kind of. I mean, the guys in Israel, who's the guy? Steinberg. Yeah. Okay.
Okay. Another question?
Grazie.
Grazie.